Welcome to lecture 2.1, focused on hybridization. In this unit, we're going to cover three types of hybridization: sp3, sp2, and sp hybridization. Talk about why we need to use this hybridization, how it works, and then in lecture 2.4, I'm going to give you a powerful trick to teach you how to quickly identify hybrids in molecules. Before we get started, let's do a quick review of the types of orbitals we're going to be dealing with. First up, we have the s orbital. This is shaped like a sphere. Generally, it's more stable, and there's one orbital per energy level, so we see typically one line with 2 electrons in it. Now, the p orbitals, there are 3 degenerate orbitals with them, and we see that each one can hold 2 electrons up for a total of 6. They're less stable than s orbitals, and they're known for having a dumbbell shape. You can see that they have 3 different orientations, these 3 degenerate orbitals. We're not going to go into too much detail there, but I thought I would just include that. So with sp3 hybridizations, for now, up until lecture 2.4, I want you to think of sp3 hybrids as the thing we deal with alkanes, when there's no double bonds, no triple bonds, just single bonded carbon. So for example, this is something like methane, which is a carbon connected to 4 different hydrogens via single bonds. Now, if I look at the base state, the base electron configuration of carbon, we see there is one s orbital with 2 electrons in it, and 3 2p orbitals with electrons in it, like such, for a total of 4 valence electrons for carbon. The problem is that when we look at the base atomic configuration, it doesn't really match up with what we observe in reality. What we see here is a carbon connected to 4 hydrogens. So we would expect, these hydrogen bonds to all be the same, that this carbon is making 4 equal bonds to them with its orbitals. However, when we look here, we see that there is one orbital that has 2 electrons in it, in the s orbital. It's more stable, almost like a lone pair. There's 2 electrons together. And then with the 2p orbitals, we see some unpaired electrons in an empty orbital. That's great and all, but it doesn't really match up with what we see here. And hybridization is what's going to help us bridge the gap. So there's a few rules we're going to deal with first. The big idea with hybridization is that we're going to mix orbitals to get what we want. And essentially, we're going to imagine that carbon knows what it's going to be binding to. So in this case, carbon knows that it wants to make 4 individual bonds to hydrogen. So one rule we're going to need to make sure we follow is that the number of orbitals that go into our mixing bowl need to be the same number of orbitals that go out. If I want to make 4 individual bonds in this case, what I'm going to do is I'm going to mix all 4 of my orbitals. So you can imagine here that there's one s orbital out of the total 4, which is like, you could say 25% s. And then you have 3 p orbitals out of the total 4, which you could say is 75% p. Now, you'll sometimes see this referred to as s character and p character. And I might refer to this later in future sections as such. But what is the new hybrid orbital going to look like? Well, we've mixed all 4 of our orbitals together, and so what we're going to have is the creation of orbitals that are 25% s, 75% p, and 4 equal energies. So these are your sp3 orbitals. Since they came from the 2 energy level, these will be 2 sp3. After the number of orbitals that went in, and you draw the number of orbitals that went out, and they're the same, then you can distribute your electrons accordingly. And now what we have is something that looks more like this: an atom with 4 orbitals surrounding it, with 1 electron in each, ready to make bonds. This matches up a whole lot better with how we observe carbon in nature. And I'll show you what this looks like in a molecule down below. But really quickly, sp3 hybrids, these orbitals are sp3 orbitals now. sp3 hybrids have a bond angle between these orbitals of 109.5. And when they're involved in bonds, we call that shape of a molecule tetrahedral. These are good things to know just in your chemical vocabulary. I'll come back to this later when we cover the quick identification in section 2.4. But what does this look like in a bigger molecule? Well, let's look at ethane. What we'll do here is we have ethane drawn with its bond line structure. And we'll look at, and we'll try to draw the orbitals that are all involved on the right there. So here is our hybridized orbital configuration of carbon-1. Now, right now, these orbitals are all unpaired, which isn't good, but we can understand this from a molecular context. So what we have is we have carbon-1 with its 4 sp3 orbitals sticking out in its 109.5 degree bond angle. These are sp3 orbitals. Now, the hydrogens, they have a 1s orbital. Right? This is not hybridized. This is just how the hydrogens are in their base state. A 1s orbital that possesses 1 electron. And so these are able to interact with the carbon electrons, and we can imagine filling those in here. So these 3 orbitals represent bonds from the carbon to the hydrogen. Now, more specifically, we could refer to these bonds as carbon sp3 bonds with hydrogen 1s. So this is saying that the sp3 orbital of our carbon, more specifically the second energy level, which will always be the case, is binding to hydrogen's 1s energy level. And that's kind of what we see here. Now, you can see that we draw these bonds without regards for that. Right? You typically don't have to worry about this when you're drawing molecules, but it's good to understand what the underlying bond actually is. Now, the last one here, this is something that can be filled in by the other carbon. Now, this other carbon is also going to be sp3 hybridized. It's also going to have its own sp3 orbitals binding to its own hydrogens. And as such, it'll be able to donate an electron to the carbon, and that's what this represents here. This is to the carbon, and these are to the hydrogens. Now, one thing I want to stress here is the concept of the sigma bond. Generally, we view these as synonymous with a single bond. But there's one thing I want to be very clear about, and that's that sigma bonds are bonds made with hybridized orbitals. And this is going to be much more important when we look at the sp2 and sp hybrids in the next section. So that wraps up the basics of sp3 hybridization for alkanes. And now it's time to look at sp2 hybrids with alkenes.